We're going to create a tree diagram for picking 2 marbles out of a bin without replacement. So let's draw the tree. Now there are 3 reds in this bin, 3 blues, and 2 greens. Okay. Person is going to reach into the bin, grabbing one of the marbles, and then removing it so that it can't be selected again. And now the person is going to reach in yet again and take another choice. Okay, so if we were to draw a tree for this situation, it would be a pretty big tree. Okay, so let's put in 3 reds, 3 blues, and 2 greens at the start. And then off of there, we're going to make our next choice. Okay, but the next choice is dependent on what happens in the first choice. So when you go to draw this tree, we don't actually want 8 branches on this red anymore because one of the marbles was removed. So we should actually only have 7 branches at the end. Okay, now no matter what I pick, there's going to be 7 choices after one marble is selected. This is all the branches. It's a lot. And let's see what could be picked next. So after you pick red the first time, that removes one of the reds from the sample space, leaving us with only 2 reds remaining. We'll have, of course, 3 blues and 2 greens. Now, these colors would be duplicated. If we chose blue the first time, you'd have 3 reds remaining, and one of the blues would be taken out of the mix. The greens would remain untouched as well. Okay, so let's duplicate this now. Finally, when it came to the greens, we'd have all our reds still in the bin and all our blues still in the bin. But there would only be 1 green at the end. And that is the complete tree for this situation. Now, what they're asking us for is the chance of getting a blue on the first pick, and a blue on the second pick. They want the first to be blue and the second is blue, so it's a sequence. Now, since I have the tree, this is easy to answer now. I just look for cases where we got blue the first time. So that would be here, and here, and here. But it would not be, these ones would not qualify. And then we want to get blue the second time as well. So that would be here, and here, here and here, and then these as well. So the answer apparently is 6. There are 6 ways to get blue then blue. Okay, so you put your number of successes in the numerator, 6, and then we got to know how many branches there are. So we could count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But instead of counting them by the slow method, let's use the fundamental counting principle, where we multiply the number of ways that the first marble could be selected. There's 8 different ways according to the sample space that they showed right here. 8 different possibilities. But when you remove a marble, you don't have 8 possibilities anymore. You only got 7. So we're going to have to do 8 times 7. There are 56 total outcomes here. And that needs to be our denominator for this problem. So it's 6 out of 56. We could find that answer a lot easier, though, than the way I just did it. To do it more easily, multiply the probability of the first marble being blue times the probability that the second marble is blue. However, I have to put in one phrase here. Given that the first was blue. Alright, so in order to do this method, just come up with 2 blanks where we'll multiply the probabilities. The chance of the first one being blue was 3 out of 8. We see that here. These are the 3 cases where the first choice was blue. Then we multiply. If the first marble is blue, there's only going to be 7 marbles left. And since you took out a blue one, if you do take out a blue one, you'll end up with 3 red, 2 blue still in the bin, and 2 greens still in the bin. So that just shows that the chance of getting blue on a second pick is 2 out of 7. So that would be the way to multiply to get this same answer without drawing the tree. That's the beauty of it. So number 2 says you have the same marble distribution in the bin, and you want the chance of pulling 2 of them out where at least 1 is not blue. So this is going to use that complement idea, where there's not going to be any 2 numbers that you could easily multiply together to get this probability. So we have to do a complement, it's called, where they're looking for the chance that at least one is not blue. So that's going to be the opposite of something. You just have to think about, what is that the opposite of? It is the opposite of both blue. Because it's either going to be one or the other. You're either going to get 2 blues in a row, like this, or you'll get at least one not blue. So those two are complements. We already said that there were 6 outcomes in the whole sample space where they're both blue. So my question is, how many outcomes are there where there's at least one not blue? Look at the tree now. If we were to look at all these outcomes and see if they qualify, right? At least one not blue. Definitely. You know, this one, red, red. There's not a blue there. There's something other than blue there is what I mean. Red, red, that qualifies. But let's go through the list. What about RB? Does that qualify as a success for at least one not blue? One is blue, but, well, they said at least one isn't blue. So it does qualify. Yeah, that's all right. And so would these then. And then red, green, they're both definitely not blue. So every single one of those outcomes qualifies. That's 7 outcomes right there. It's actually going to be a pretty big number. You know what it is? It's everybody except six. Yep. All these qualify, at least one not blue. The only ones that don't qualify is here. This is both blue, so they don't qualify. But this one would, and these would. So what is the chance, really, of getting at least one not blue? You use 6 out of 56 somehow. What do you do with it? You gotta subtract it. How many check marks did I just make? Yep. How many outcomes were there in all? 7 times 8. 56 outcomes in all. I say that 6 of them are blue, blue. Only those 6, though. So how many outcomes have at least one not blue then? Yeah, 50. That's right. The way you solve it is you say, okay, if the chance of getting both blue is 6 out of 56, then the chance of at least one not being blue is 1 minus that. It is 50 out of 56. Yep.